So good morning and good afternoon and good evening, everyone. I'm Caterina Vigliar, a postdoc at University of Bristol. And today I'm going to talk about our recent work on the generation and processing of reconfigurable photonic entangled states for quantum computing applications and error correction encodings. So working in quantum computing, one very early realizes that in order to perform useful tasks, there is the need of controlling a large number of entangled qubits. And also, being an experimentalist, one suddenly realizes that there are inevitable errors that occur that need the introduction of error correction codes that in turn expand even more the number of qubits requirements. And thankfully, in the photonic platform for quantum computing, silicon technologies can really come in our help, offering a high precision, stable, and large-scale circuitry needed for controlling such large-scale systems. So here I will show you an instance of a silicon photonic processor that embeds error correction encodings in the form of a specific class of entangled states called graph states. So we will focus on experimental realization of error correction embedded in the framework of measurement-based quantum computing that we've heard already a few times today. So in the measurement-based paradigm, the computation relies on an initial generation of a graph state, an entangled state that can be represented graphically by a graph object, where the qubits are represented by nodes and the quantum correlations are represented by edges between them. So as graph states are both the resource for the computation and have a direct mapping to quantum error correcting codes for defining logical qubits, the measurement-based paradigm can intrinsically facilitate a fault-tolerant architecture. And there are a few ways to achieve fault tolerance in the measurement-based paradigm. So here, one way is to use graph codes. So logical states and operation can be protected in this framework by replacing each physical qubit of the lattice with an error correction code, such as a stabilizer code, represented here as an orange bubble. And each qubit in this bubble is entangled with its companions depending on the graph code used, and also entangled to neighboring bubbles depending on the topologies of the logical graph state wanted. So in this case, you can see a regular 3D cluster state. So this results in a new graph definition in which each vertex is now a logical qubit encoded in multiple physical qubits represented in blue, which can be eventually faulty. And the nice thing about this is that the overall state of physical qubits can still be represented as a graph state. So in the end, what you want to do to perform some sort of error-protected computations is to build a technological platform able to generate and process these specific entangled resources in somehow a feasible way. So just to give you some numbers, if one wanted to be able to arbitrarily reconfigure the entanglement between a fixed number of available qubits, it would come across a huge number of different graph topologies. So only for 6 qubits here, you can see there are 112 different graphs that can be grouped in 11 different entanglement classes. So clearly, if one wanted to switch among all these different entanglement scenarios to achieve different types of computations and different error correction encodings in a photonic platform, bulk optical realization would be totally impractical. What we would like is instead a quantum photonic chip with integrated photon sources and electronically reconfigurable components, which can be reprogrammed to generate photons with different entanglement properties. And if the chip circuitry is general enough, the different graph states can be generated in software without physically changing the hardware. And silicon photonics really offers all the optical components required for manipulating light. So waveguides, beam splitters, MZIs, crossers for routing light, and even single photon sources with very close to ideal ones being recently reported. And all these components have very good performances, even compared to bulk optical components, but have the additional advantage of being miniaturized, thus very easily reproducible, and live in a stable environment. So here, for example, you can see in a few millimeters squared, you can have tens of experiments with all the components being present. So what I'm going to focus today is a 4-photon experiment that leverages on the quality of this platform to build a reconfigurable 8-qubit experiment. So in this case, we rely on the generation of 4 high-dimensional photons, as shown here with dotted blue and red arrows. And the chip can be decomposed for simplicity in 3 modules, so I can give you a better understanding of the photonic circuit. So we have a QD pair source stage as a black square, an entangling stage as a black dot, and a measurement stage in blue and red squares. So let's see these stages individually. In the sources stage, QDs are created by mapping into the path degree of freedom of a photon. So in our case, a 4-dimensional system is created by placing a photon in a superposition of 4 waveguides. By simultaneously mapping 4 photon pair sources, we create one entangled pair of 4-dimensional photon, labeled A and B for simplicity in red and blue. So now each of these 4-dimensional photons can be mapped into a 2-qubit system, thus creating effectively an entangled state of 4 qubits. And in our experiments, we have 2 of these structures. Now, in order to create a globally entangled state, the missing correlation between the 2 pairs must be performed. So this can be done at the entangling gate stage, in which the 2 blue or the 2 red photons can be fused through carefully constructed mode swap gates realized by Mach-Zehnder interferometers. These are basically post-selected fusion gates. And by tuning the headers in this stage, we can create different graph structures like the 8-qubit star graph here, equivalent to a G at Z state of 8 qubits, where the shadowed regions here always indicate the different photons they belong to. And finally, the photons enter in the measurement stage, where arbitrary 4-dimensional projective measurements can be performed through a triangular array of Mach-Zehnder interferometers. So in these measurement schemes, we can compile different actions. So both non-local and local rotations, such as intra-qubit control Z operations, and local complementation operations. And we can embed also vertex deletions in forms of Z measurements. And on top of that, we can also measure the qubits in arbitrary local basis. So we can perform any kind of measurement-based type of protocol with it. And all of this is squeezed in a few millimeters squared in the following overall circuit that totals 8 photons, 8 integrated sources, more than 200 passive optical components, and more than 40 active components. With active components, I mean phase shifters here. Here I wanted to show you some examples of entangled states that we are able to generate. This is an example of a 4-dimensional, 4-partite entangled state with 72% fidelity with the ideal state, obtained with partial tomography techniques. This is basically the starting resource to encode our qubit state, a selection of which is reported here with states up to 8 qubits. And they all have fidelities above 72%. This level of reconfigurability allows us to create not just these states, but even more exotic ones, like these ones shown here, for example, among which there are some useful for error correction applications, like the so-called crazy graphs. So crazy graph structures can equip linear graph states with error correction, where a repetition code associated to each column of the 2-dimensional physical lattice replaces a single physical vertex, resulting in a linear logical graph. And such states are suitable for photonic fault-tolerant architectures, as they can correct both computational errors and high levels of qubit loss. And among these states we can achieve, there is a 2x3 crazy graph instance shown here, which can encode a 3-qubit logical line, where each qubit is encoded in a 2-qubit repetition code. And to test its effectiveness in correcting phase flip errors, we perform process tomographies of some measurement-based 1-qubit gates. So now if we have a line of 3 qubits, we can perform arbitrary 1-qubit rotations along the x-axis by choosing the measurement basis on the central qubit. And the initial and the final measurement perform the 1-qubit state initialization and readout, respectively. And crucially, the error protection is carried out throughout the whole computation, because there are 2 qubits at every stage. So we can do that on a physical 3-qubit line, so with no error correction in blue, or a logical 3-qubit line in yellow, and compare the two cases. So as shown through these bars here representing the process tomography fidelities, on average, the crazy graph performs better than the simple line of 3. So in the previous example, we were just using a 2-qubit repetition code, which can only detect the presence of 1-qubit error. More resilient error correcting code can be realized by using larger repetition codes. And we implement such codes using the so-called branched states, equivalent to a 3-qubit linear graph, where the middle vertex is now protected against phase flip errors via either a 3-qubit linear graph, where the middle vertex, where there are 3 qubits in the middle vertex, or a 5-qubit repetition code. We test their performance by performing a state teleportation from the leftmost to the rightmost qubit of the graph, and performing the identity operation by a next measurement in the middle. So we check their resilience to noise by deliberately applying errors in the physical qubit of the middle column. So you can see the 3 different scenarios of 1 errors happening or 2 errors happening in the middle column, or all physical qubits being affected by an error on the right plot. And you can see in all cases, high redundancy that we introduce, so for example, the B3 case or the B7 case, result in an enhanced fidelity of the teleported state, indicating a higher tolerance to computational errors. And for more details, you can have a look at our paper down here that just got on arXiv a few months ago. And moreover, we tested our device in the implementation of some rudimentary quantum algorithms. So here I'm going to show you the results for an implementation of our rudimentary measurement-based version of the phase estimation algorithm. So the goal of the phase estimation algorithm can be stated as reconstructing a phase acting on an input quantum state. So here we're implementing an iterative version of the algorithm, which iteratively infers in reverse order the bits of the binary expansion of the phase we want to learn, using the logical circuit represented here, where the rotation angles are adaptively chosen during the inference process. On the left, you can see its standard circuit scheme, and on the right, the mapping to the measurement-based formalism. Again, using a 3-qubit line, and we can do that in the same case as before, in a simple physical form or logical form. So we test this algorithm experimentally by applying a range of phases with 3-bit precision, as shown here on the bottom. And we showed, together with the results for the logical case, the results for the physical qubits for comparison, so the top black bars. And we can see that we observe 9 errors on 24 in the physical case against 1 error on 24 for the logical state, resulting in almost in more than 30 percentage point increase in success rate. So these results really show that even rudimentary codes like this one can give advantages in near-term application, not just in fully fault-tolerant devices. So this is mainly all from me. Here, just wanted to show you a little teaser about more exotic states we can generate with our high-dimensional architecture. And these are called hypergraphs, where instead of having just one qubit-qubit interactions with normal edges, we also have higher order correlations represented by loops around multiple qubits. So for example, a 3-qubit edge represents a Toffoli gate to a control-Z operation. And you can imagine treating these states with upper edges as computational resources as well, as in the measurement-based paradigm we were using simple graph states. And it has been proposed that these more complex resources could be beneficial for measurement-based quantum computing applications, allowing for simplified measurement bases, and maybe having a potential for correcting correlated errors, but this is still ongoing research. And we showed a couple of examples of these graphs and the working principles of MBOC with hypergraphs. But for more information, again, I refer to our latest paper down here. And with that, I would like to thank all my collaborators around the world